All right, good afternoon, everyone. It's noon on Wednesday. That means it's time for the Iowa Learning Farms Conservation Webinar. I'm Matt Helmers with Iowa State University and Director of the Iowa Nutrient Research Center. Excited to be back to moderate this webinar. And seems like it's been a long time, and it has been a number of weeks since I got to moderate. And gives me great pleasure to introduce our speaker today. Dr. Sushant Mehan, that is an assistant professor and extension water resource engineer at South Dakota State University. He's going to talk to us today about what 100 years of climate data means for water resources practitioners. As always, if you have questions, feel free to type those in the chat box, and we'll get those to Dr. Mehan at the end of his talk. And with that, the virtual floor is all yours.
Thank you, Matt, for the invitation, and I'm very excited to present my talk today to all the people who are attending this webinar. So the topic of my talk today is what 100 years of climate data means for water resources practitioners. And I'm thrilled to be part of this 2024 conservation webinar series brought to you by Iowa Learning Farm, which is celebrating its 20 years of promoting sustainable agriculture and conservation practices. We need something like that. So over the next 25 to 30 minutes, I will be talking to you through an analysis of past 100 years of climate data, specifically focusing on how long-term climate changes in the climate variables, especially temperature, air temperature, and precipitation and drought have impacted the water resources in the United States, particularly in the Great Plains region. As water practitioners, understanding these trends is kind of crucial to help us make informed decisions about water management, irrigation practices, and conservation strategies, especially as we face these increasing challenges from climate variability. This data provides a powerful lens to better understand the long-term shifts that are reshaping how we manage and conserve water resources. I encourage you to ask questions and engage with as we go along. And with that, let's get started. Okay, so the graphic highlights on the slide significant drought events in the contiguous United States over the last century. Compare the mean drought extent. We can see drought episodes spanning from 1900 to 2014, with yellow arrow indicating the percentage of the continental United States affected by these droughts during these periods. The noticeable episodes include the drought from July 1928 to May 1942, commonly known as Dust Bowl, where the mean drought extent reached 29.7% of the United States. The 1950s drought from July 1949 to September 1957 had the highest mean drought extent of 33.3%, making it most severe in the terms of area affected. Most recently, the drought from June 1998 to 2014, the longest in the history, is just covering 28.7% of the United States, indicating that even in this time, the large-scale drought remained a significant concern. The thing that to be noticed here is from 1976 and onwards, there is an increasing trend up there. So these numbers demonstrate that droughts in the US have varied both in duration and extent, but they all highlight the need for the vigilant water resource management and planning. We know from the research, we just saw the timeline for the droughts, that this region, that in the United States, we are experiencing noticeable changes both in the factors like temperatures and precipitation. Temperatures are generally increasing while the precipitation patterns have become more variable. This has included more frequent and intense precipitation events in some areas, along with longer dry periods in other areas. However, the question here is, how have long-term trends in precipitation and temperature changed across the Great Plains over the past century? And with these shifts in temperature and precipitation, there are a lot of implications. Changes in precipitation affect the availability of the surface water, groundwater recharge, and the soil moisture. which are all very crucial for agriculture, industry, and municipal water storage in the region. Increased temperature also lead to increased evapotranspiration rates, further stressing water resources. If these trends continue, water scarcity could become an even more pressing issue, influencing everything from the crop production to the health of a local ecosystem. So my second question for the talk today is, what are the implications of these changes on water resources in the Great Plains region? As I'm very specifically talking about the Great Plains region, why I am choosing this specific region, not the entire US. The reason is the Great Plains region is very critical for the US agriculture. And this slide highlights two key things why it is so important. First, look at the map on the left, which shows the percent of the farmland per county across the US. As you can see, the Great Plains, particularly in the states like Nebraska, Kansas, South Dakota, and North Dakota, are shaded in the darkest green. This indicates that more than 70 to 90% of the land in these countries is devoted to farming. The vast amount of the agricultural land here makes this region a major contributor to the food production in the United States. Whereas on the right, we have a table displaying total cash receipts from all agriculture commodities in 2022 provided by the USDA. For the Great Plains states highlighted here, the total agriculture revenue was around 128.7 billion, which is a significant portion of 536.6 billion in the total US agriculture revenue. That was my motivation why I'm focusing on the Great Plains while doing this kind of analysis. So the slide here outlines the methodology that my team is using to do climate analysis study, which focuses on the long-term trends in precipitation, temperature, and aridity in the Great Plains region. We are using NOAA daily climate data from the ground-based station spanning from 1924 to 2023, that spans 100 years, to capture both the precipitation and temperature data, including maximum and minimum temperature separately. We also calculate two critical indices, climate indices, standard precipitation evapotranspiration index, which help us assess the drought conditions, and the aridity index to measure overall dryness. We analyze data over multiple time periods, 100 years, 50 years, 30 years, and 10 years to understand the short-term and the long-term trends. These time periods are analyzed on monthly, annual, growing season, and seasonal basis to capture variations in different time scales. For trend analysis, we used statistical tools like Mann-Kendall test and Sain slope to determine the direction and the magnitude of the trends. Finally, we compare these recent trends to the long-term trends, which give us insight into whether the region is becoming more or less arid over the period of time. Whereas on the right, you will see a table showing a length of the record of the station we analyzed. We have around 212 stations with over 100 years of the data, and nearly 1,000 stations, which provides a robust data for 10 years and ideal for the trend analysis of this kind. So getting into the results, the first thing I would like to discuss with you is the spatial analysis of average growing season precipitation totals across the Great Plains, covering a total region of 1.9 million square kilometers. We are looking at the precipitation data for the 4 time periods. The figure on the extreme left from 1924 to 2023, spanning 100 years, 74 to 23, 50 years, 1994 to 2023, 30 years, and 14 to 23, the most recent decade. The color scale on the right indicates the precipitation level in millimeters, ranging from less than 400 millimeter in yellow to 850 millimeter or more in dark red. As you can see that over a period of time, the southern and central parts of the Great Plains, particularly Texas, Oklahoma, and Kansas, experiences low precipitation total during the growing season, representing the dominance of the orange colors and the red colors in the figures. These areas consistently receiving less than 650 millimeter of the precipitation. Looking at the table at the bottom, which shows the percent of the Great Plains under different precipitation classes over the past 100 years, over the 100-year period, 12.3% of the Great Plains region fall in 650 to 850 category. while only 0.1% was receiving more than 850 millimeter of the rainfall. However, in the most recent 10-year of the period from 2014 to 2023, the percentage of the Great Plain receiving 650 to 850 millimeter increased to 14.8%. And the areas with more than 850 have grown to 3%, showing a slight upward shift in regions receiving high precipitation totals. These map and the table demonstrate changes in the precipitation patterns over time, which are important to understand how climate variability affects the growing season and ultimately the agriculture productivity in the Great Plains. The slide presents here the results of the analysis of extreme temperature days. So I'll start with the bottom left sentence over there. The 99th percentile of the maximum air temperature is 38.9. That is for the entire Great Plains, 7 states. But we picked the number 45 degrees Celsius, considering that it is beyond 38.9, and just to see that how many days over a period of year comes out to be more than 45 degrees Celsius. So the graph on the left shows you the number of days per year where the maximum air temperature, daily maximum air temperature surpassed 45 degrees Celsius from 1920 to 2023. As you can see, there have been periods of significant increase in extreme temperature days, most notably in 1930s and 1950s, and especially in the recent years. The 1930s recorded some of the highest numbers of the extreme temperature days with 23 days in 1 year. After a period of relatively fewer extreme days during the mid-20th century, we again saw a sudden rise in 1950s and a consistent increase from 2000 onwards, culminating a peak of 30 days having temperature more than 45 degrees Celsius in 2020. Let's look at the table on the right, which highlights distribution of the extreme dry days by month. Unsurprisingly, extreme temperatures are more frequent during the summer months. 53% of the extreme heat days occur in July, 23% occur in August, 22% occur in June, and only 2% of the extreme heat days occur in other months of the year. So these findings actually show that the occurrence of the extreme temperature events is not only increasing in frequency, but is also heavily concentrated in the peak summer months, which could have significant implications on water resources management and agriculture in the Great Plains region. The analysis on this slide presents the number of dry days and the wet days in the Great Plains region, covering around 1.9 million square kilometers of the Great Plains region. Starting from the graph A on the top left, this shows the number of the dry days per year from 1920 to 2023. A dry day is defined as a day with no measurable precipitation. The graph reveals some variability across the year. While the number of dry days generally fluctuating between 290 to 320 per year, in recent decades, we observed that there is an upward trend of the dry days, especially from 1980 onwards. Whereas the graph B, we can see the deviation from the average number of dry days over the same period. The positive bars are indicating that there are more dry days in that particular year, whereas the negative shows the fewer dry days. The deviation has shown more extreme fluctuations, especially during the period from 1930s and 1950s, known for significant drought events. The spatial map, the C figure on the middle, is basically showing the distribution of wet days across the Great Plains over the last decade. The wet days are classified into categories with color scale indicating the number of dry days from 25 to 40 with light yellow in color up to 100 and 150 days. That means wet days in dark red. Most of the region experiences about 40 to 55 wet days per year, covering 63% of the Great Plains. Only 3% of the area experience more than 100 wet days annually. The table is further broken down to 6% of the region has fewer than 40 wet days per year, 63% falls between 40 and 55 days range, while 17% experiences 55 to 75 wet days. The Great Plain predominantly sees fewer than 55 wet days per year, with an increasing number of dry days, especially in the recent decade. And this could have serious implications on water availability and agriculture activities in the Great Plains region. So this slide basically presents the results of the first climate index that I talked about, standardized precipitation evapotranspiration index, which measures both the drought and the wetness trend across the Great Plains over the period of time, 100 years, 50 years, 30 years, and 10 years. The focus on each chart corresponds to different SPEI timescales. So SPEI 1 and 3 are more corresponding to meteorological drought. SPEI 6 is more agricultural drought prone. SPEI 12 is a hydrological drought indicator. So starting with chart A, we observe that over a period of 100 years, 6.81% of the Great Plain region showing a decreasing trend in SPEI1. And however, this trend increases dramatically over shorter time frames. That means in 50 years, we saw 24.18% of the area showing decreasing trend. In 30-year period, 22.74%, and in the last 10 years, 18.03% of the area shows the downward trend. In chart B for SPEI3, we saw something similar. The 100-year period shows a decrease in 10.17% of the area, rising to 32.52% in the recent decade, indicating significant drying in the recent decades. Chart C, SPEI6, continues this pattern with a substantial increase in the area affected by a downward trend from 11.08% over 100 years to 44.14% in the last 10 years. Finally, in chart D, for SPEI 12, the percentage of the area showing a decreasing trend is even higher, 50.91% of the Great Plains region exhibiting increasing dryness over the last decade. This is a significant increase from 11.33% seen in the last 100 years. This results clearly show an upward trend in drying conditions across the Great Plains, particularly in the last 10 years. The shorter the SPEI time scale, the smaller the area affected, but the overall trend toward the drying condition is consistent across all the time periods and the SPEI scales. There are concerns because of this on the water availability, agriculture, and ecosystem health in the Great Plains. The second climate index I wanted to talk about is aridity index for the Great Plains. For the different time periods, the figure on the extreme left is for 100 years, 50 years, 30 years, and 10 years. The aridity index is used to measure the dryness of the region, with lower values indicating more arid conditions. The four maps show the spatial distribution of aridity index for each time period. A is indicating 100, B 50, C 30, and D is for the most recent 10 years. As we move from 100-year to the 10-year, we can observe a notable increase in the aridity in semi-arid region, particularly in the southern parts of the Great Plains, including Texas, Oklahoma, and Kansas. The blue areas indicating more humid conditions are shrinking over time, while the red and the orange areas representing arid and the dry humid regions are expanding. In the last 10 years, approximately 8.6% of the Great Plains has shown a decreasing trend in the AI, indicating that the region is becoming more and more drier, which is a significant concern for the water resources. The table at the bottom further breaks down the percentage of the Great Plains that falls into each class of the aridity index. In the 100-year period, 1.9% of the area is classified as having an aridity index less than or equal to 0.5, indicating arid conditions. In the last 30 years, it reaches to 7.4%, and in the most recent 10-year period, 9.1% of the Great Plains is classified as arid, suggesting a significant drying trend. The data shows an increasing trend towards aridity in the Great Plains, especially over the last few decades, and it has some important implications on water availability and agriculture productivity. So what do all these mean for water resources practitioner? To illustrate what it means for water resources practitioners, so this slide illustrates a declining trend in renewable freshwater resources per capita over time, comparing the United States and the world average from 1961 to 2020. Renewable freshwater resource refers to any internal flows from sources such as rivers, rainfall recharge groundwater within a country. The red line represents the United States, while the blue line represents the global average. As you can see, both the lines show a steady decline over the past several decades. In 1961, the United States had around 13,000 cubic meters of renewable fresh water per capita. By 2020, the number had dropped to just under 9,000 cubic meters. The global average started at 9,000 cubic meter per person in 1961 and has decreased to 5,000 cubic meters in 2020. There are several factors that could affect this downward trend. To count those factors, number one could be the population growth. As population increases, the available water per person decreases. Could be changes in climate. Could be climate variability, changes in precipitation pattern, more frequent droughts, higher evaporation rates affect the replenishment of the freshwater sources. Could be over-extraction of the water for agricultural, industry, and domestic use, further depleting these renewable resources. The point to highlight here is the gap between the US and the global average is narrowing, which suggests that while US still have more fresh water per capita than the world average, the rate of decline is significant and highlights the importance of the water conservation and better management practices in the realm of climate variability. The data highlights the global challenge where the per capita freshwater resources are decreasing, and the prompt here is to adopt sustainable water management strategies to meet the demands of the growing population and under the face of the climate variability. About the water quality, this slide illustrates the relationship between catchment nitrogen retention capacity and discharge under varying hydrological conditions, with a particular focus on 2 years, 2018 and 19, both marked by the drought condition. Just to let you know, this particular study was done in Germany, and they tried to develop a kind of a relationship between what actually impact the nitrogen retention capacity in catchment. So this illustration is from that study, and the source is in the link below. On the x-axis, we have discharge, which represents the amount of the water leaving the catchment area, while the y-axis shows the nitrogen retention capacity, indicating the ecosystem's ability to retain nitrogen and prevent it from being transported downstream. The black curve demonstrates the inverse relationship. As discharge increases, nitrogen retention capacity decreases in a catchment. The two highlighted points, 2018 and 19, fall on the left side of the curve, illustrating how drought conditions marked by even the low discharge are associated with a reduced nitrogen retention capacity. This suggests that during drought condition, even though there is less water flowing through the system, the catchment's ability to retain nitrogen diminishes, which could lead to increased nitrogen losses during the post-drought recovery period. On the opposite end, the higher discharge events typically corresponds to a further reduction in nitrogen retention as the system becomes more overloaded with water, reducing the ability to retain nutrients effectively. Overall, this graphic is providing a critical insight into how droughts and extreme weather conditions impact nutrient cycling in the catchment. It highlights the importance of monitoring both the drought and the discharge levels to better manage nitrogen or other nutrient retention and minimize the quality degradation. I think this particular slide set a very good stage for the next week talk by Matt. So we will talk about it later. What are some feasible solutions? We talked about a lot of problems. So what could be the possible solutions? As we are concluding this discussion, it's clear that we need some solutions. And one of the possible solutions could be the water smart farming. Precision farming that could play a pivotal role in addressing the growing challenges posed by the climate change, water scarcity, shifting dry regions. As we can see with the movement of the 100th meridian, especially if the figure on the right, that dividing line between the dry western and the wetter eastern United States has shifted 140 miles eastward over the past 100 years, and it's projected to move another 100 miles by 2100. To combat these challenges, the possible solution that my lab could think of is the water smart farming that integrates a lot of critical effort, that integrates a series of critical efforts. Number one is the water conservation and water harvesting techniques that could be essential to manage the limited water resources efficiently. Improving irrigation accessibility and improving water use efficiency. We can make every drop count, especially in the areas facing drought or having reduced precipitation. Enhancing water infiltration and reducing runoff ensures the water stays in the soil, directly benefiting the crop growth. Furthermore, minimizing soil evaporation and boosting crop productivity ensures that agriculture system remains resilient in the face of drier and hotter climates. I think these strategies are not just beneficial, but necessary as we look forward towards the future of the farming in the changing climate. The map to the right, I've already told you that illustrates that how the dryness is on the move, emphasizing even more the need of the proactive solutions like the water smart farming to maintain the productivity and sustainability in the agriculture. I believe adopting these practices will be very critical for the farmers and policymakers alike to ensure that agriculture remains sustainable, resilient, and productive, even as we face the shifting climatic changes. So with that, this is my contact information. If you would have any questions, if you think something really appeals you more and there's a collaboration opportunity, please feel free to reach out. With that, Matt, I'll hand it over to you.
Okay. I think the next slide should be the CCA. There we are. If you watch this webinar live and want to earn a CCA CEU, please email Elena Whitaker, ALENAW @iastate.edu by 5 o'clock today and include your name, the name you entered to watch the webinar, and your CCA number. Again, Elena Whitaker, ALENAW @iastate.edu. Go to the next slide. We can. And folks, if you have questions, feel free to type those in the chat box. We should have time for those when we get through these last couple slides. If you watch this webinar live and are willing to fill out a voluntary demographic survey, we'd really appreciate it. Only one survey is needed for all 2024 webinars. So if you've done that, thank you very much. If not, and you're willing, please go to iowalearningfarms.org/survey or scan the QR code. And then the last one is we do have a webinar next week. And I'm going to talk about some of our 2024 data, nitrate leaching, where we had rain after dry conditions. So I think it, as Sushant mentioned, maybe kind of relevant to some of this. So couple questions that have come in and should have time for more as well. As you've looked at this, yeah, there is a good one. This is a good place to start. Can you clarify what SPEI stands for and the practical implications of what it means?
So SPEI is one of the climate index. The full form is Standardized Precipitation Evapotranspiration Index, and it is annual precipitation over the potential evapotranspiration. So it is a ratio of, this is how it is calculated. And there are different time scales of SPEI. As I mentioned in my slide, it is SPEI 1, SPEI 3, 6, and 12. These are indicators of wetness and dryness conditions. So if you are more interested in just meteorological drought, SPEI 1 is to look at numbers from SPEI 1. But if you're looking at agricultural drought, like you want to focus on difference in vegetative growth of corn versus different phase of corn growth, so SPEI 3 and 6 are good indicators. Whereas if you are interested in hydrological droughts, the stream flow, the surface discharge, and other things, SPEI 12 could be a good indicator.
Okay, great. As you were looking at the Great Plains areas, are there certain areas that might be getting worse than others?
So right now, our assessment is we are doing it for the entire Great Plains. It's very difficult to focus on one particular region, but to our surprise, what we are noticing is the the western part of Texas is not having a lot of climate data. So means whatever we are indicating is based on the ground-based station, because we saw a lot of bias in the gridded set. There are Prism data set and there are other data sets which we could use. The first challenge is they are very coarse resolution, 4-kilometer grids or 1-kilometer grids. So we will be answering that question, Matt, but we do not have a right answer right now.
All right, cool. Another one is that one of your last slides, it showed kind of the the shifting in the that one, kind of the dryness on the move. The makes me think about water resource planning for some of the Great Plains states where we use where there's a lot of irrigation, and whether, I guess maybe two parts, is this are these kind of features, or this kind of movement of this dryness zone being considered in water resource planning for irrigation water use, and should it be if we see changing maybe changing weather patterns or changing dryness patterns?
If I understood your question well, so just to confirm your question, so you are stating that would these changes drive the decision for the irrigation management in future?
Yeah, I guess my question is, if is a little bit bigger picture thinking about this. If some of these areas are getting drier, how might that impact irrigation water use? And should that start to be factored in as we think about a kind of a sustainable water use model in these areas?
Okay. So I believe I have not checked the entire data set on irrigation, but we have that irrigation data set which we are looking at. So I think the trend towards more precise irrigation has already been started, variable rate irrigation and all those things. So I think this dryer shift has already moved that kind of a needle to decide, means to plan about those irrigation things. Means we are not more focused on gravity and more uniform irrigation now. So in order to increase the irrigation efficiency, especially in Nebraska, we are seeing a lot of variable rate irrigation thing happening. And I think we should consider this shift more in our planning, and we will see those kind of changes in near future.
Okay, great. There were a couple other questions that came in. Are you seeing any seen any, or what differences might you be seeing in terms of water resource impacts for crop production versus livestock production?
Wow. Oh,
I think that's an interesting question because a lot of this area would be pasture, that pretty reliant on pasture for the livestock production and how that might impact forage forage biomass.
I think the question is great. To the best of my knowledge, is I have not divided my data set based on the use, but what I am seeing is the producers are encouraged to find an alternative source of water for their livestock rather than sending them out to open creeks or small streams. I'm not means here in South Dakota, we are paying them to do so, which falls under the umbrella of the SRAM project that I am doing.
Okay.
And with this thing, moves with more climate variability, I think there will be more pressing concerns that they should look for other alternate source of water for livestock. But it may take a long time. I do
Yeah.
not know how it would look like, but it will be very different from crop to the livestock. So
Yeah.
I have to think more about it.
Okay. Yeah, I would just think that's an interesting question because if those areas get drier, um, do we have to change stocking density? So not just the water for drinking, but for water for the pasture ground to produce biomass. Um, there was another question here. Western Colorado seems to be getting wetter. Any thoughts on that?
Not actually. Means
Okay.
I have except the way the Rocky Mountains work. So that is the only thing I could think of that it's more driven by the topography and the relief features rather than anything else. So that's where the eastern is more reflection of drought versus the western Colorado, which is getting more and more wet.
All right. I think that addresses the questions. Sushant, thank you very much for the presentation. Again, folks, if you need a CCA CEU, please email Elena Whitaker, ALENAW at iastate.edu by 5 o'clock today. With your name, the name you entered to watch the webinar, and your CCA number. Again, feel free to tune in next week. And as always, just to let you know, the webinars are recorded and they're on the Iowa Learning Farms website or on our Iowa Learning Farms webinars YouTube page. So with that, thank you again, Sushant, and we'll see you soon. We have the Drainage Research Forum coming up
Right.
tomorrow here in Ames. So I hope everybody has a great day.